Chapter 7, Lesson 4, we are going to learn how to write and graph exponential growth functions. This covers standard CED.A.2, where we are creating and graphing equations that include two or more variables. The first thing that we're going to look at is what is an exponential function? An exponential function has to be in the form of y equals a times b to the x power. And what you have to know is a can't be 0 and b has to be bigger than 0, but it cannot be 1. Okay? You also know that this is not linear. So when you're looking at a table and you're trying to determine, is this a linear function or is this an exponential function, the first couple of things that you're going to do is you're going to first identify, do my x values always increase by the same amount? And you can see here every single one of these increase by an addition of 1. And then you look at the y values. Since the x values increased by 1, you look at the y values. And to go from -4 to -1, we're adding 3. Is that addition of 3 consistent all the way throughout? You can continue on and you can see that yes, it is adding 3 all the way throughout. Now, if we go back on how to calculate rate of change or calculate the slope, you're going to do the change in y over the change in x. So my slope here, my rate of change would be 3 over 1, which is 3. So because this one has a slope, okay, notice my exponential function equation has no m value, there is no slope. So we know that this one has a slope of m equals 3, which means it cannot be a exponential function. It's a linear equation, so this would be a linear equation rather than exponential. Now my second table, again, I start off by asking, did each of these increase by 1? Yes, they did. So because they increased by 1, then I start looking at my bottom values. And what I see here, to go from 2/9 to 2/3, it's a multiplier of 3. To go from 2/3 to 2, it's a multiplier of 3. To go from 2 to 6, it's a multiplier of 3, and so on. So because it is a multiplier rather than an additive here, this is going to be an exponential function. Now we're also going to learn how to look at those tables and come up with what is the exponential function, what is the rule. But the first thing you need to do is you need to be able to identify, is it linear or is it exponential? So you've got your addition or you've got your multiplication. In order to write a rule, you're going to follow 3 steps. The first thing, like I talked about, is determine if the growth is linear or exponential. Okay, so was it multiplied or was it added or subtracted? The second thing is find the value of a by finding the value of y when x equals 0. So that wordage might be a little bit confusing, but I will show you in an example on the next slide. But again, you're going to find the value of a by finding the value of y when x equals 0. And then once you do that, then you just write your function. So let's take a look at what this actually looks like. So here is our first table. We look at the x values, we can see that every single time it's increased by 1. So that's good. The next thing is what happens to go from 2 to 4? Well, I could think I'm adding 2, but is that adding of 2 consistent in the rest of the table? No. So what's my other option? My other option would be to multiply by 2. And then did it multiply by 2 all the way throughout? Yes, it did. So that multiplying of 2, that's something that's very important. So if we look at this, we know that step 1 says, is the growth exponential? Yes. And it increases by a multiplier of 2. So that represents in our equation of y equals a times b to the x power. We know that because that multiplier is 2, then b equals 2. So whatever your multiplier is, that's what your b value is. So we're going to substitute 2 in for b. So now what we have is we have y equals a times 2 to the x power. From here, we're going to find the value of a if x equals 0. So we're going to substitute 0 in for x. And the reason for that is because anything to the power of 0 equals 1. So our goal is to get this portion to 1 so we can solve for a. So now we have y equals what, or a times 1. And we also know that y equals 8. How do we know that y equals 8? Well, if we look back up here at our table, when x was 0, which is what we substituted in for the variable x, y was 8. So that coordinate has to stick together. 0, 8 has to stick to 0 together. So y equals 8. So we have 8 equals a times 2 to the 0 power, which is 1. Therefore, a equals 8. So now we can remove the x and the y, the 0 and the 8, and we can rewrite our function, our rule. So we know our rule is y equals 8 times, y equals 8 times 2 to the x power. So when we look at this, remember the 2 comes from your multiplier right here, and the 8 came from solving your a value. All right, let's take a look at another one. So again, does x increase by 1? Yes, it does. What does y increase by? It's a multiplier of 3 every single time. So because my multiplier is 3, now I know that my b value is 3. So we now have y equals a times 3 to the x. And then we look for when x is 0, what's y? So because x is 0 and y is 27, our equation goes from this to 27, because 27 is y, equals, we don't know what a is, times 3, because that's our multiplier, and then x is 0, so 3 to the 0 power. Now we're solving for a. So you have 27 equals a times 3 to the 0 power is 1. Therefore, a equals 27, which now means that when I write my function, we want y to stay as y, we want x to stay as x, but we want to replace the a and the b with a specific number. So we just found out that a is 27 times b was 3 to the, 3, so times 3 to the x power. Okay, now notice that you cannot do 27 times 3, because when you follow order of operations, your exponent would be done first. So we leave it in this form because we need to know what x is in order to simplify it before multiplying by 27. So our final answer is y equals 27 times 3 to the x power. All right, now sometimes we have fractions involved, and that's perfectly fine. I always like to look for my multiplier within the whole numbers. So what's happening from 1 to get to 2? Well, it's either adding 1 or it's multiplying by 2. So then I look at the 2 to the 4, definitely not adding 1, so I'm multiplying by 2. Okay, if I take 1/2 and I multiply it by 2, I get 1. And if I take 1/4 and I multiply it by 2, I get 1/2. So my multiplier is 2, which means b is 2. My a value we have to solve for. So we're going to do y equals a times b, but we know b is 2. So we're going to write 2 in for b to the x power. So now we're going to substitute when x is 0, what is y? So y is 1. So we have 1 equals a times 2 to the 0 power. Well, 2 to the 0 power is 1, so 1 is equal to a. Therefore, my equation, my function is y equals 1 times 2 to the x power. Do you need that 1 there? No. But if you want to easily identify your a value and your b value, you want them there. But another sufficient answer would just be y equals 2 to the x power. We also need to be able to graph our exponential growth. So you've got two parts here. You've got to write your equation, but you also have to graph it. So this is actually our first example, and we solved that first example, and we got the function y equals 8 times 2 to the x power. So if I was given my equation, but I didn't have the table, I would create the table. But the table is given, so now all we need to do is plot our points. So we have negative 2, comma 2, so 2 left, 2 up. You have 1 left, 4 up. You have 0, 8 up. And then 116, that's not going to fit, okay? But what you need to know is if this were going to continue, you would always cut that point in half. Every time you go left 1, you'd cut it in half. Now, can you cut a number in half and ever get 0? No. So what you need to know here is this is going to get as close as it possibly can to the x-axis, but it will never touch the x-axis. It's exponential growth because it is getting bigger from left to right. So growth is bigger from left to right. So from here, you're just plotting your points, and you've got your graph. Our second equation that we solved for was y equals 27 times 3 to the x power. So we already solved this. Based on the table, we calculated it. Now all we do is we plot our points. So negative 2, comma 3. Negative 1, comma 9. Okay? What you need to know again is this is going to continue to get bigger and bigger and bigger. It's going to steep up, but as it shrinks down, it is never going to touch that x-axis. So it just continues to get bigger and bigger and bigger, and it's growing from left to right. My third example here was negative 2, comma 1/4, negative 1 1/2, 0 1, 1 2, and 2 4. Again, getting closer and closer and closer, but never touching, and it goes up really, really fast. Now, exponential growth is very important when it comes to money. Anybody that has ever put money in the bank, or maybe you put it into a certificate of deposit, a CD at the bank, you will be told what % your money will grow. Now that's a little bit different than stocks and bonds or stocks and mutual funds, because your rate can fluctuate based on what the stock market does. But a CD or a bank account is going to have a constant rate of growth. And in part 2, I will show you how you use the growth formula to calculate how much money you would have after a specific amount of time. So come back for part 2.